Hello and welcome to part 4 of this lecture on group 17 elements of halogens. The next one that we're going to talk about is the reactions of solid halides with concentrated sulfuric acid. You must be wondering why is it insisted that we use solid halide salts? I mean, halide salts mean, say, sodium chloride, say, potassium iodide, calcium fluoride, etc. Okay, but we want those ionic salts in their solid form, not in aqueous solutions. The reason is if you take them as aqueous solutions and you react, you find that with the amount of water that is present, because it's aqueous, the observations are easy to be missed. Okay? The gases that are produced are also highly soluble in water, so you don't see them coming out. So we'd rather do these with the solid halide salts and concentrated sulfuric acid. So, I mean, it could be any halide salt, preferably something that is from group 1 or group 2, because those ones are highly soluble. Okay, the ion can separate out easily, so kind of makes it easier. Okay, so with the chloride salt, so let's say, for example, I take sodium chloride solid and I add a sulfuric acid, concentrated sulfuric acid to it, you find that it produces dense white fumes. We know dense white fumes most probably is going to be the hydrogen chloride. So you take it and you test it with damp indicator paper. Okay, you find that the indicator paper would turn red, okay, blue to red, that is acidic. If you're using a universal indicator paper or a pH paper, you'll find that it turns red, showing that the gas is strongly acidic. Now, what happens is the sulfuric acid reacts with the sodium chloride. It produces sodium hydrogen sulfate, NaHSO4, okay, sodium bisulfate as we call it, and it produces hydrogen chloride gas. The hydrogen chloride gas is the one that is seen as coming out as white fumes. What's interesting to note is that the sulfuric acid has got two hydrogens. The sulfuric acid is essentially just converted into HSO4. H2SO4 is converted into HSO4, if you see this, right? So H2SO4 is converted into HSO4 minus in the sodium hydrogen sulfate. That means only one H plus is missing. So sulfuric acid is acting as the acid in this case, right? While the sodium chloride is acting as the base, because it accepts the H plus to form these hydrogen chloride. So the first one is just a it's an acid-base reaction. Okay, it's acid-base reaction. If you look at the oxidation numbers of every species that is present on either side, you'll basically find that it's the same. Okay, why did I only mention about sulfur and chloride? We'll see that a little later. But we pretty much know that hydrogen and oxygen usually, and sodium usually have just one oxidation state. I mean, generally hydrogen is +1, sodium is +1, oxygen is -2. So nothing much has changed there. Okay, so I was just looking at the ones that do exhibit variable oxidation states and see what happens to those. Okay, that's the chloride salt. With the bromide salt, okay, with the bromide salt, so you take, say, potassium bromide or sodium bromide. Yeah, I've kind of spoken here with the sodium bromide, but it could be potassium bromide, calcium bromide, anything. Okay, so when concentrated sulfuric acid is added to sodium bromide solid, initially you see a dense white fume. That basically means you have HBr being given out. So the same reaction is happening. The first reaction is acid-base reaction, so no difference there. Again, the sulfuric acid just loses one proton. Okay, but the oxidation numbers remain the same. It's +6 for the sulfur on both sides, -1 for the bromide on both sides. Okay, but a little later, okay, if you just observe a little later, a little longer, you find that red-brown vapor is also seen. And we know that red-brown or orange vapor is typically bromine gas being given out. And that is because the hydrogen bromide further reacts. The hydrogen bromide that you got over here, that you produced over here, further reacts with the sulfuric acid to give you sulfur dioxide, water, and bromine. And the bromine that you see is the red-orange vapor. Now, this one is a little interesting because you find that the bromide here is in -1. Here it is 0. The sulfur is +6. Here it is +4. To balance it, you're going to need 4 oxygens. So say 4, say there's 2 oxygens over here. So 2 more oxygens to make it 4. That's 4 hydrogen now. Make that into 4 hydrogens, 2 bromines, and it's done. Okay, So, so this is what we see, and this is a redox reaction. The bromide is getting oxidized from -1 to 0. The sulfur is getting reduced from +6 to +4. Okay. The very obvious observation would be for that of the bromine, which is a red-brown or red-orange vapor. I mean, we can't miss it. If you want to test for sulfur dioxide, you can test it with a filter paper dipped in dichromate. Yeah, the filter paper dipped in dichromate will react with sulfur dioxide in another redox reaction to go from orange to green, and we know that. Okay, so that can be used, but then usually, unless you suspect for sulfur dioxide, you will miss it because it's not a visible observation. It's one that you do because you are aware of the presence of this gas. Okay, that's it. So this is a redox reaction. Here, the bromide is getting oxidized, the sulfur is getting reduced. All right, so it's a redox reaction. With the iodide salt, okay, with the iodide salt, it gets even weird. So let's say I take the sodium iodide, potassium iodide. Potassium iodide is actually a more common iodide salt than sodium iodide, to be honest. Okay, you'll find potassium iodide in every laboratory. Sodium iodide is incorrect. So when you take the sodium iodide to the potassium iodide and you do this reaction, you basically have a bunch of observations to make. First, initially, you will have the dense white fumes. Obviously, that is because of the hydrogen iodide produced, but then a little later, you'll see purple vapors. You will basically get the foul, stinking smell, what is called as a rotten egg smell of a foul gas. You will also, after everything is done and you look at the bottom of the test tube, you'll find that there's a yellow solid left deposited. Okay, so many observations. The first reaction, obviously, is an acid-base reaction. Yeah, let me just put that here. The first reaction is obviously an acid-base reaction, where the sulfur is, where the sulfuric acid is just losing a proton, okay, to the sodium iodide, forms sodium hydrogen sulfate, hydrogen iodide, and the hydrogen iodide is white fumes. And then it gets interesting because hydrogen iodide can actually react in 3 different reactions with sulfuric acid, okay? It produces sulfur dioxide. It produces sulfur dioxide, water, and iodine. This is similar to the one that we saw with bromine, okay? So this is +6, this is +4, -1, 0. So this is a redox reaction, and the iodine gas is the purple vapor that you see. But it can also form, rather than forming sulfur dioxide, it can also form sulfur in which the oxidation state is 0, okay? Elemental sulfur, solid sulfur, which is seen as a yellow solid at the bottom of the test tube. The iodine is 0. Or the sulfuric acid can react with the hydrogen iodide, forming hydrogen sulfide, in which case the sulfur is in an oxidation state of -2. The iodine goes from -1 to 0. Okay, so 3 different reactions. If we try to balance this, there are 4 oxygens, 2 oxygens over here, so 2 more oxygens needed. That makes it 4 hydrogen. 4 hydrogen, thank you very much. Now that is 4 oxygens. So oxygen is only present over here. So 4, that makes it 8 hydrogen. 2 hydrogens makes this, make this into 6 more hydrogen to make it 8 hydrogen. That means I'm gonna need 3 iodines. All right, that's done. The next one, okay, 4 oxygens. So say 4 oxygens. That makes it as 8 + 2, 10 hydrogens, right? 8 + 2, 10 hydrogens. There are 2 hydrogens over here. So I'm gonna need 8 more hydrogens to make that 10. That means 8 iodine, 4 iodine. Okay, so that's the balancing, but let's focus on the important bit. The thing is, if you look at it, the halide ions, okay, the Br- or the I-, they are getting oxidized to the elemental state, Br2 or I2. That's an oxidation reaction. And we know that by definition, if something gets itself oxidized, it is your reducing agent. So we understand that in all these 3 redox reactions, the I- is acting as the reducing agent. Okay, The I minus is acting as the reducing agent, which means the sulfuric acid is the oxidizing agent. That's a different story. But the focus is not on the sulfuric acid here. Okay, so the I minus is acting as the reducing agent. Now, if you look at it, the bromide reduced sulfur from +6 to +4. Okay, the bromide reduced sulfur from +6 to +4. The chloride was not able to do that. So obviously, by that extension, the fluoride would not have been able to do that either. So there's no point bothering about the fluorine right now. But the iodide reduced the sulfur in the sulfuric acid from +6 to +4, from +4 to 0, all the way up to -2. All right. So it went from +4 to, from +6 to +4 to 0 to -2. So at the end, it's gone from +6 to -2, which is what? Jumping about 8 units. Okay, 8 oxidation units. That tells us that the iodide is the strongest reducing agent of the 3 that we've seen here. Okay, I mean, if they ask you if the acetatide is going to be stronger or weaker reducing agent than iodide, you understand that as you go down the group, it increases. As a result, acetatide is going to be stronger than that. And the fluoride is going to be the weakest, right? The fluoride is going to be the weakest. Okay, so this makes for an interesting comparison, okay, on the reactivity and the oxidizing, reducing ability. So if I have to write the general equations for the redox, I can say fluorine gains electrons to turn into fluoride. Right? Fluorine gains electrons to get converted to fluoride. Bromine gains electrons to get converted to bromide. And iodine gains electrons to get converted to iodide. Now, this is what we have. And you know, the halogens, right? The halogens are all gaining electrons because remember, they have 7 electrons in the last shell, need 1 more, Okay, so all the halogens are gaining electrons to become reduced and get converted to the, to the halide, right? The halogens gain electrons. So let's say X2 plus 2 electron to get converted to X minus. So the halogens gain electrons, get reduced. Okay. So the halogens gain electron to get reduced. As a result, they are oxidizing agents. Halogens, that is your X2, gain electrons to get reduced. They are oxidizing agents. Okay, and we know that fluorine gains electrons rather quickly, and that's the reason why it reacts very, very quickly. Okay, fluorine is the fastest to react. Okay, is the fastest to react. Hence, it is the strongest oxidizing agent. Okay, it's the strongest oxidizing agent. So the oxidizing ability decreases down the road. Okay, so when you come from here to here, the oxidizing ability decreases down the road. So they become weaker oxidizing agents. Okay, so oxidizing ability decreases down the group, so they become weaker oxidizing agents. The explanation for as to why fluorine gains electrons the fastest is there in IGCSE chemistry, where we talk about how the fluorine atom is the smallest, and hence it would, I mean, you can also talk about it in terms of your topic 3, okay, chemical bonding, where you talk about how fluorine has got the highest electronegativity. No, you actually need to talk about electron affinity, which is there in A levels. Sorry. Okay, but then you understand that fluorine has the smallest atom. It has got only 2 shells, which means the least shielding effect. So the nuclear attraction for the valence electron, or the electron outside, is much higher. So it gains the electron more readily, okay, making it the most reactive. And the converse of that happens in the case of iodine. Now, if you look at the halides in the reverse reaction, so that is what you need to understand, right? So what I'm talking about here in the case of the halides is in the reverse reaction, the backward reaction. The halides lose electrons to get oxidized, which means they are reducing agents. Okay, reducing agents. Now, I minus, as we've just seen, the iodide. Okay, the iodide, not the iodine. The iodide is the I minus ion, right? It's the I minus ion. So the iodide is the strongest reducing agent. Okay, hence you basically find that the reducing ability, the halides, not the halogens, halides is the X minus ion. The reducing ability of the halides increases down the group. That means the fluoride is the weakest, while the iodide is the strongest if you're just looking at the 4 traditional halides, okay? So you go down the group like this. Okay, you go down the group like this, you find that the reducing ability increases. It becomes more reducing, becomes stronger reducing agents. So this one is in the 0 oxidation state. This is in the -1 oxidation state. So you understand that the X2 is an oxidizing agent. It gets itself reduced. While the X minus is a reducing agent because it gets itself oxidized. Okay. That's a very, very important part of this lesson, and it's often tested. Okay. So see you guys in the next session, and hopefully we should be able to wrap this topic.